Welcome to part 1 of this explainer. Today, we're diving straight into the article Power Electronics Course with QSPICE Episode 05 to unpack the hidden nanosecond mysteries of dynamic steady-state efficiency in power MOSFETs. If you design power electronics, you already know that managing efficiency is the absolute core of what we do. But while steady-state losses are relatively straightforward to calculate, the dynamic regime is where the true benchmark of your design skills is tested. Let's get right into it and look under the microscope at what actually happens when a power device switches on and off. Okay, let's dive into this. Taking a macro view of our circuit here, we're looking at a standard QSPICE schematic designed to analyze dynamic behavior. We've got a 24-volt DC source powering the drain of a silicon carbide power MOSFET, right, through a 10-ohm resistive load. And down at the gate, we're driving this device with a perfectly square 10 kHz PWM wave. It pulses from 0 to 23 volts with a 30% duty cycle. It's a very standard typical setup for evaluating voltage, current, and instantaneous power during a transient state. Now, if we run a standard 2 millisecond transient analysis on this circuit, here's what we see. That green trace is our drain voltage, the blue trace is the drain current, and that red trace down at the bottom, that's our instantaneous power dissipation. Honestly, at this macro scale, everything looks incredibly clean, right? The switching appears perfectly instantaneous. It's totally ideal. The voltage drops, the current rises, and if you look at those flat lines, it seemingly produces zero power losses during the actual transitions. It looks exactly like a theoretical textbook example. But make no mistake, this is a macro illusion. Because as engineers, we know that perfect right angles don't actually exist in real-world components. There is this gritty, messy reality hiding inside those perfectly straight vertical lines. So I have a question for you. What happens if we zoom in, say, 500 times on just one single rising edge of this waveform? What is really going on in those tiny fractions of a microsecond when the device is told to turn on? Well, the illusion is completely shattered. By zooming in, we reveal a 13 nanosecond rise time transition, which we denote as TR. This is that critical exact moment the MOSFET switches from off to on, passing right through the linear region. Notice how the drain voltage doesn't just drop to 0 instantly, and the drain current doesn't just instantly jump to 2.5 amps. Instead, they overlap. And since we know power equals voltage times current, this simultaneous overlap generates a massive instantaneous power dissipation. We're looking at a peak of over 14 watts of heat generated in literally just 13 nanoseconds. To truly master your thermal management, you absolutely have to be able to calculate this energy loss. So here is the dynamic power equation that governs this exact phenomenon. The formula is power equals 0.5 times input voltage times output current times the sum of the rise time and fall time times the switching frequency. Now, I want to explicitly clarify that 0.5 factor right at the beginning. It's not just some random constant we threw in there. It actually represents the literal geometric area of a triangle, 1/2 base times height. The base is the time the transition takes, and the height is the massive peak power created by that overlapping voltage current triangle we just talked about. So, the crucial point here is how all these variables interact in a modern high-speed power system. Dynamic power losses scale linearly. Think about it. If you double your switching frequency to shrink down your magnetics, you are directly doubling your switching losses. If your edge transition times are sloppy and slow, your thermal losses scale up linearly. And remember, these dynamic losses don't just replace your steady-state losses. They have to be combined with your standard RDS-on conduction losses. This whole compounding effect is exactly why high-frequency designs require absolutely meticulous thermal management strategies right from day one. And honestly, this brilliantly illustrates the massive gap between ideal switching and real-world physics. In a textbook, switching is instant, but in reality, as literally anyone who's ever debugged a smoking prototype knows all too well, you don't just have clean 13 nanosecond overlaps. You've also got parasitic capacitances, PCB trace inductances, ringing, and overshoot ripples that complicate the waveform even further. And this is exactly where a tool like QSPICE shows its unique and powerful strength. It lets you inject those parasitic inductances and distributed capacitances directly into the simulation. That means you can accurately capture these non-ideal waveforms way before you ever print a physical circuit board. By integrating this instantaneous power over time right there in the software, you can definitively measure your dynamic efficiency during the design phase. But, we've only looked at the rise time today. What kind of hidden destructive power spikes are waiting for us when the device actually tries to turn off? Well, we are going to uncover the secrets of the fall time in part 2 of this explainer. Until then, remember the golden rule of power design. Compute before building with Engineering World Company.